Hello everyone, in this video we will talk about deterministic pushdown automata. Just as in finite automata we had deterministic and non-deterministic, in pushdown automata as well we have deterministic as well as non-deterministic pushdown automata. And here is what makes a pushdown automaton deterministic or non-deterministic. If there is a state from where I get two choices of states that I can move to, based on my input symbol and stack symbol, then I say that there is some non-determinism involved in this. So that is how a non-deterministic pushdown automaton is made. And the definition that we wrote in the last video for delta, if you remember, we wrote that delta was from Q cross sigma union epsilon cross gamma, which was our stack alphabet, and from here we said that it went to Q cross gamma star. In case of a non-deterministic automaton, what's going to happen is it's going to go to 2 power Q cross gamma star. So what we are saying is that there might be some cases where I have something like this. We have gamma of q comma a comma x is equal to a set which is some q1 comma x1 and another element is q2 comma x2, which means that from a given state based on the same input symbol and the same stack top, I can move to two states. So remember that if I have something like this, if I have something like a comma z goes to some x1 and I have another one which says a comma a goes to x2, this still has not broken determinism. So all this has done is it has said that if I have the input symbol a and the stack top is z, then move to this state which is, let's say, q1, and secondly, if the input symbol is a but the stack top is capital A, then move to this state which is q2. So that's all I'm saying when I say something like this, and this still hasn't broken determinism. To break determinism, I need to have some situation where I have multiple choices. So the formal condition that we give for an automaton, a pushdown automaton, to be deterministic is the following. We say that for it to be deterministic, delta of q comma a comma x union delta of q comma epsilon comma x should be at most one element. So this should be a singleton. So what that means is that from a state, if I have, let's say, something like this, I have a comma a, and I have another transition which is epsilon comma a, then once again I'm going to have a dilemma here when my input is a. Should I take this path right here or should I take the bottom one? Because if the stack top is capital A, and in that case I can move to either this state right here, or I could just not consume the input symbol and move here. So that is why we have this condition. So this is how we formally write the condition for a deterministic automaton. So I hope you have understood the difference between a deterministic and a non-deterministic automaton. There's one more thing that we need to talk about. So in the last video I mentioned that the acceptance by final state and acceptance by empty stack was becoming equivalent, but to be honest, that's an inaccuracy. We shouldn't really call it equivalent. What was just going on was that every input string that we considered was getting accepted by both a final state and an empty stack. So that's what was happening. But when do we say that the acceptance by empty state, empty stack and acceptance by final state is actually equivalent? We say that when we have something like this. So if I have a language L and a pushdown automaton exists which accepts it by empty stack, then we can always draw another pushdown automaton. So let's call the first one PDA1 and PDA2. So for the same language, I can always draw a pushdown automaton which will accept the string by final state. So this is actually when they are equivalent. And what happens is, in case of a non-deterministic automata, these two do become equivalent. So if there is a pushdown automaton for language L which accepts L by empty stack, there also exists a pushdown automaton for L which accepts it by final state. But in case of a deterministic automaton, these acceptance conditions aren't equal. They aren't equivalent, which means that it need not necessarily be that I can always have a deterministic automaton which accepts the same language by empty stack as well as final state. So that's what the equivalence means. And one more thing that I feel is very important to mention is that when we looked at DFA and NFA, we said that they have the same expressive power, which means that we can always convert an NFA to an equivalent DFA or vice versa. But that's not true with deterministic pushdown automata. Non-deterministic pushdown automata have more expressive power than deterministic pushdown automata, which means that the NPDA is a superset of DPDA. So if you have a deterministic automaton for a deterministic pushdown automaton for some language, then you can always have a non-deterministic automaton for that language. But if you have a non-deterministic pushdown automaton for a language, it does not mean that you will be able to come up with a deterministic pushdown automaton for the same language. So these two do not have the same expressive power. NPDA are inherently more powerful than DPDA. So that's the last point that I want to mention. That concludes our discussion on deterministic pushdown automata. What we'll do in the next video is we'll see how we can convert any given context-free grammar to a pushdown automaton. So we'll see that in the next video. In the meanwhile, you know the drill. Give the video a like, share it with your friends, and hit the subscribe button if you haven't already. See you next time.